Alright, chemistry. Let's do this. I know it's been a little bit. I was behind on lab videos, so hopefully if you're seeing this, you can also see a lab video in the labs topic going through the, what's it called? Oh my goodness. Cooling curve for water lab. What I ended up doing with that, just because it's like not necessarily something I would want to watch. I walk through what we did. I have an example data table in there, and you should be able to complete that before Friday evening. I'll extend the timer on that because I was late putting up that video. The only other thing that we were kind of doing this week was making sure that we're ready for the test on Friday. All right, hopefully you didn't forget. You've been looking at the announcements on my CBA. Last week I talked about it, so here it is. We're almost to Friday. What I want to talk about and what I want to look at specifically is down here at the bottom of page 60. There are some equations down here that I wanted to do in a second lab, but time got away from me. Well, no, not so much the time got away from me, just I know the timing for that lab, and that's a 2-day lab, and I felt better about doing the cooling curve lab to talk about temperature change and phase change, the lack of temperature change during a phase change. I prefer to be able to get through that basically in its entirety than have to take 2 classes to do the other lab. So here we go with the bottom of page 60. I'm looking specifically at like these 3 bullet points down here. And the reason I'm looking down here is because there are some equations down here that we have not used, right? One of these equations we have looked at, we have seen before, right? And I'm going to list them out the way that they're listed out on your reference table, and there's another intention behind that. So Q equals M times C times delta T. So this is the equation that we used before, right? And these are all heat equations. These are all how to solve for a certain amount of heat, how to solve for a certain amount of energy, how many joules does it require, right? The wording of the question would be like that. You'll want to use this, use this if the temperature changes, right? Because that's what delta T stands for. Delta T is change in temperature. Remember that delta T is final minus initial, right? Your ending temperature minus the beginning temperature. The problem is, and this is, from the lab, during the lab, you took water and you put it in super cold ice, ice that was below the freezing point of water. So the water in the test tube actually gave its energy away to the ice, and as a result, it froze. But as it was freezing, the temperature stopped changing. So there was no temperature change during a phase change, which means that delta T would be 0. So if I tried to do Q equals mc delta T, but delta T is 0, that means that heat is 0, and that's just not true. During a phase change, there is still heat transfer. That's why the phase is changing. There is energy moving from one place to another, but it's not kinetic energy. It's potential energy, and we have to use different formulas and different information. Sneeze. No, don't have to sneeze. We have to use different formulas and different information in order to solve that question. So the next equation that you see up here, right, there is no temperature change during a phase change. Q equals mc delta T cannot be used because Q will be 0. So to calculate it, you're going to use a different formula. It's on the reference table. It's on the last page. It says Q equals M times HF. Now, as a reminder, HF is the heat of fusion, and fusion means melting. So use if melting spelling. There we go. All right. The last equation is this one here. And again, I'm doing this intentionally. I'll explain why. It says Q equals mHV. HV was the heat of vaporization, so of boiling, which means that this is the equation to use. Use if boiling, right? Now the reason I use this order, and I'm intentional about it, I want you to look at how they're ordered. It's top, middle, bottom. Oop. I was going to try to zoom out and see if I have the reference table page nearby. I'm inclined to say that I do not. So let's throw it in here. Chem reference table. I need this page. Let's insert this page. Oh, or is it gonna... It's doing the thing where it's not letting me. I think the problem is I've started to kind of add too many images to this, and it's like freaking out on me a little bit. Alright, let me try this. Oh wait, give me that back. What if I want to center it like right here? You know, that's really not where I wanted it. Can I move it? If I do this, if I just closer, that'll do. Close enough. It actually lines up pretty well. So again, Q equals MC delta T, just like I wrote it. Q equals MHF, and Q equals MHV. I want you to notice that it goes top, middle, bottom, right? There we go. The top equation is what you use if the temperature changes. The middle equation is what you use if it's melting. The bottom equation is what you use if it's boiling, right? And that applies here. I'll use the top equation for a temperature change, middle equation for melting, bottom equation for boiling. Top, middle, bottom, temperature change, melting, boiling. And the reason I bring up those phrases or those terms is because if you see a question, like we do on the top of page 61, mixed heat calculation practice, right? And you have to determine the amount of heat, like how many joules, right? We're calculating heat. You need to know not just to use the heat equations, but need to know which one to use, right? So what I'd like you to do, take a couple minutes here, use the reference table, try to solve these 4 questions. Figure out, do I need to use the top, middle, or bottom equation? And then plug in numbers, all right? I'll give you a second. I'll probably hit pause. You're back, my bad. I was trying to snack. I'm a little hungry. Okay. So you're back. You did you've done these questions. So let's do some math, right? So the first question, how many joules are required to melt? Look, they used the word melt. That means middle equation. Q equals MHF, which means it's 100 grams times HF. By the way, HF is listed here, HV is listed here, but if you remember, they tell you what they mean, tells you specific heat capacity, heat of fusion, heat of vaporization. Hopefully you remember that C is on the front page of the reference table. The heat of fusion and the heat of vaporization are also both on the front page of the reference table. Right? Table B, the second table, it's on the middle left of the reference table, very first page. So what I'm looking at is 100 times 334 joules per gram. If I do that math, I get 33,400 joules. Right? Question number 2, how many joules are required to heat 200 grams of water from 25 to 90? That's a temperature change. That's the top equation. Q equals MC delta T, which means 200 grams times 4.18 joules per gram degree Celsius times 90 minus 25 is 65 degrees Celsius. This is, I don't remember this one. It's 54,340, but I'm going to check. 200 times 4.18 times 65. 54,340. I don't think that's what I said before. All right. How many joules are required to boil? Boil means bottom equation. Q equals M times HV. This is how we figure out how much heat is needed to boil this water. It's 150 grams at 2260 joules per gram, which means this is 339,000 joules. That's how much energy it takes. Notice, it's not that much more water than before, but it's like 10 times as much energy, right? It's much more difficult to boil water than it is to melt ice. That should kind of make sense. That should be like your experience. You can hold it in your hand and you can melt it. It would take much more energy. You need to put it on a stovetop in order to boil it at normal pressure. And then finally, number 4, how many joules are given off when they're cooled from 25 to 0? Change in temperature. Temperature changed. That's Q equals mc delta T. So that means 120 times 4.18. This time, it's negative 25 because it's dropping. We're going to get a negative number, and that's okay because the joules are given off. I believe this was negative 12,540, but again, I will check my math. So 120 times 4.18 times negative 25, negative 12,540 joules. All right. That was one of the things that I wanted to make sure of. Make sure that you're able to understand when to use each equation, how to, where to look for the equations. The only other big thing that I want to mention is kind of like how to interpret and what to say if you're asked, like, what is occurring on this time interval? What is occurring on this line segment, right? So if I look, what is occurring between each of the following? This chart is the cooling curve for a gas, which means I start here with a gas, it cools down until it changes phase. Temperature stops changing. There's a phase change. It is a gas, it's turning into the next lowest, which is liquid, so this is condensation. And then right here, we start cooling down the liquid until it hits another stopping point for temperature. Well, that's the freezing point. So we're going from liquid to solid, and then down here, we're cooling the solid down. Right? So what is occurring between 3 and 7? Well, that's condensation. What is occurring between 12 and 15? Well, that is freezing. Just for the sake of argument, let's say that you forget condensation is a word, or you forget that freezing is a word. But you know it's a phase change from liquid to solid for freezing. You know it's a phase change from gas to liquid for condensation. Well, then just write phase change from liquid to solid, or phase change from gas to liquid. If you can't remember the actual word, write what you know is happening. All right? From 15 to 16, I'm cooling a solid. Right, from 7 to 12, that middle section, we're cooling a liquid. And from 1 to 3, we're cooling a gas. We're always cooling something down, right? So that's kind of how to label those sections. It's not like particularly difficult. It's not particularly like, wow, that was, it's nothing like that. I just wanted to make sure that you knew kind of what to say in those cases, because I don't think it's always obvious like how to address that, right? The very last thing is actually the very last thing on this page, Mr. Summers, and I leave this on here because deposition or its opposite, sublimation, are always a question. Deposition is gas to liquid. It's the phase change. Nope, that's wrong. Okay. Deposition is a gas to a solid. Sublimation is its opposite. That is a solid to a gas, right? That definition or that phase change is almost always a question. And those are actually two words that you should try your best to remember. Or at least recognize. Recognize that, like, if you see deposition, like, oh, as a phase change, it's one of the weird ones, it's gas to solid. You're depositing it. You're putting it down, right? Sublimation, it starts with an S, so it starts as a solid and it goes to a gas. All right. Now, the test on Friday is actually going to be more thermochemistry than other stuff. It's 30 questions. I would wager, I can't tell you exactly how many are on thermochemistry, but there are quite a few questions on thermochemistry, more than there would normally be, just because I really want to make sure that this stuff is solid. I can still ask about protons, neutrons, electrons. I could still ask about ionic versus covalent compounds. I could still ask about gas laws. Could still ask about other stuff, but it will be a lot of this thermochemistry just because I want to make sure it's really good. You'll have an hour to take it. It'll be 30 questions. Use your reference table, use a calculator. Do your best on it. If you're not sure on something, try to eliminate as many answers as possible and guess. And don't change your answer unless you go back and look at it and say, that was completely wrong. Otherwise, stick with your first answer. All right. Please email me with any questions. Otherwise, I will assume that everything is fine. And I will see you kids next time. So until then, take care.